to Alex, so you can have them, and if you are interested, of course, you can have a further read. And if you have any questions, you can send me an email or ask now. Thank you very much.
Thank you. I mean, I think now the audience know, like, to be a good physical modeler, you are not only to be a good geotechnical engineer. You should also be a mechanical engineer, a photographer, and also a farmer, maybe. So, but because of time, I think we save the question for the last, and we directly let Dr. Stefano start, and in the end, we ask the question all together, I think. So, thank you, Amin.
Yep.
So our next presentation will be given by Dr. Stefano Muraro, and the topic is pit testing of regional dyke on soft soils in Netherlands. But before we start, I will give a short introduction to Stefano. So Stefano obtained his master degree in University of Twente in Italy, and after that he obtained his PhD in University of TU Delft. And his research mainly focused on the laboratory testing and constitutive modeling and soil structure interaction. And currently, his main research interest is basically on the organic soil, which is like a pit, which is very important in Netherlands. And I think that's it. And the floor is yours, Stefano.
Thank you very much. May I just ask you if you can see my presentation full screen and if you can hear me clearly?
Yes, very clear.
Okay, thank you very much, and apologize for not being able to be there in person, but due to teaching periods here in Delft, I was not able to join you. So as one said, my name is Stefano, I work at Delft University of Technology, and I would like to follow a bit the presentation of Susanne and Amin to show a recent field testing on a regional dyke here that we perform also together with Amin in the Netherlands. Before starting going inside the case, I would like to show a bit what was the relationship, or what is the relationship between soft soil and the Netherlands. I call it a sort of long-lasting relationship. As you can see, the western part of the country on the left-hand side is actually built on soft soil. And in particular, we have peat and organic clays. And these soft soil obviously are creating some problem, especially for what concern land subsidence, therefore settlement, long-term settlement creep, but also for serviceability and stability problems of infrastructure. And you can see here on the bottom right that we have a failure of a small polder dyke, and this failure happened in 2021, so only last year in July. And one of the most tricky problems in the Netherlands is the behavior of peat. Now, for those of you who might not be familiar with peat, it's an organic soil, which is especially composed by partially decomposed organic matter, in particular leaves, roots, and fibers. You can see here multiple levels of fibers on the picture. And peat is an exceptional material because it has a porosity of 90%, so basically it's almost pure water. It's extremely compressible, so lambda upon isotropic compression is at least 2. But at the same time, even though it's so compressible, it has a very high friction angle, which is at least above 40 degrees. And as I mentioned before, it has a multiple level of fibers, which can range from few millimeter to few centimeter long. Now, one of the most important problems in the Netherlands is actually understanding how this material behaves at the field scale. So how can we understand how peat and peat's interaction with other soil layers is actually occurring in the field? So we started investigating this problem in 2015 in the field scale. And there was a unique opportunity. There was this polder, which is a small island in the Netherlands, that was given to TU Delft together with Deltares as a site where we could perform a controlled dyke failure. So we were allowed to inundate the polder and to perform a dyke control failure. So when we start designing basically the controlled dyke failure, we're starting from the field investigation. So we focus on this small triangle that you can see here on the top right, and we were allowed to bring this small triangle to failure. So here you can see a map of the field investigation that we perform. We perform a series of CPT, so comb penetration test, in 3 basically cross sections, section south, center, and north. And together with CPT, we also retrieve samples from boreholes, in particular 6 boreholes, located below the crest of the dike, at the toe of the dike, and in the polder site. Now, I want to show you here a typical stratigraphy of soft soil in the Netherlands. So you see that we have the dike material. You see a lot of scatter in the sleeve friction in the correcting core resistance. And this is because of the fact that the dike material was extremely heterogeneous. There were gravel, sand, and clay, which basically comes from all the material that was available 500 years ago when this dike was actually built. Underneath the dike material, we have a pit layer, so extremely compressible. You see that the pit layer at the toe of the dike or in the polder is quite thick, is 2.5 meter thick. But if you go below the dike material, of course, there was a lot of compression, and the thickness of these pit layers is actually only 1 meter. Below the pit layer, we have a clayey silt layer, as well organic. We will see later on what does it mean organic for this type of material. And eventually, deeper, we have a clay layer and a sand layer. Now, after having performed basically the field investigation, so we were able to clarify what was the layering of our subsoil, we basically move our attention to the laboratory scale and to perform a characterization of this material, both in terms of index properties, compression behavior, and also shearing behavior. Now, here is some of the results from the soil characterization. I would like to show you what does it mean dealing with soft soil in the Netherlands or in other parts of the world. So as you can see here, we have the in situ water content. So the water content in dike material is increasing with depth, ranging from 0.2 to 0.6. But when you enter in the pit layer, the water content goes to 10. So pit layer basically is almost purely water. And at the same time, the clayey silt underneath has a quite high organic content of about 1. So please keep in mind this profile of water content that you can see in this picture, and we will try to compare later on how this profile can also be linked with the profile of the failure surface. Another important feature of soft soil and organic soil is actually the organic content. And here is basically the organic content that we determine from the laboratory. So the organic content, the dike material is quite low, but in any case, it's quite important for this material, is about 3 to 4%. Organic content in the pit layer goes to 80 or 90% due to the presence of fibers. And then underneath the pit layer, we have the organic content in the clayey silt, which is about 5 to 8%. So in any case, there is a various, let's say, distribution of organic content, which will especially affect the compression behavior of this material. Now, together with the water content, organic content, we can actually estimate what is the bulk unit weight of our soil. And you see that the dike material, due to this heterogeneous nature, has a bulk unit weight which ranges between 14 kilonewton per cubic meter to 20. Especially the pit materials are quite striking because you see a bulk unit weight basically 10, which is just above water. And eventually the clayey silt a bulk unit weight of 14, extremely soft soil. Now, if you transfer this low unit weight into effective stress, you ended up basically understanding what is the challenge of testing such materials also from a laboratory point of view. Because if you want to characterize this soft soil, especially on the polder side, you should be able to perform laboratory tests with a vertical effective stress, which is about 5 to 10 kPa. So it's extremely challenging from an experimental point of view dealing with soft soil, because not only the fabric of the soil, like fibers, but also because of the very low effective confining stress that these soft soil are actually exposed in the field. Now, another important feature of characterizing the initial stress state of our soil, which is fundamental then to design the failure test, is also defining what is the overconsolidation ratio in the field. So you see here the overconsolidation ratio that we derive from oedometer test. The dike material is slightly overconsolidated. The pit layer underneath the dike material, due to the higher confining stress, is normally consolidated. But it's quite interesting to see what is the the overconsolidation ratio of the pit and clayey silt at the toe of the dike. Despite the fact that there was no mechanical loading in this site, you see that there is in any case an over-consolidated ratio about 3:4. And this OCR is not mostly coming from mechanical loading, but is actually coming from interaction with the atmosphere. So cycles of drying and wetting basically gave this over-consolidation ratio to this material. Now, I want to show you, due to constraint of time, only some results for what concerns the shearing behavior of this material. And I will show you some of the results from triaxial and dyke simple shear test on these three different layers: the dyke material, the pit layer, and the clayey silt layer, which are the main three layers that were involved inside the failure mechanism. So the dyke material, as I mentioned multiple times, is extremely heterogeneous. It consists of silt and sand with some also gravel inside, OCR between 1 to 2, and a bulk unit weight of 18 kilonewton per cubic meter. You see here an inclusion of silt inside basically a sample, so you clearly see how heterogeneous these materials is. And here you see the results in terms of deviatoric stress versus mean effective stress of a triaxial and drain compression test that we perform at different confining stress. Now, one of the most important features of this material is it has an initial contractant response, so we have a positive development of excess pore water pressure. But after, even especially a large strain, we have dilation. So we have a negative excess pore water pressure. But this dilation is not accompanied by softening, so the deviatoric stress is not decreasing, but it's actually increasing. So this is a specific feature, especially of silty material, tested at very low confining stress. And when you increase the confining stress to 40 or 90 kPa, you see that basically we are switching off this tendency to dilate. So basically the dyke material was characterized with a friction angle at critical state of about 36 degrees. Now, for what concerns the pit material has been tested especially in direct simple shear. And you can see here that a very low confining stress is 5 kPa in order to mimic the effective stress in the field. Also, the pit material shown initial contractant response, followed by a a dilation accompanied with increase in the shear stress. But already at 10 kPa, which is already a quite high stress for pit, the material is basically contracted. And the estimated friction angle for this material is about 42 degrees, which is extremely high due to the presence of fibers. And then eventually moving downward towards the clayey silt material, which is the layer underneath the pit. This material has a friction angle 38. It has a much higher component of clay compared to silt, so you don't see this dilation accompanied by an increase in the deviatoric stress. But you clearly see a more honest, let's say, response. So you have an initial elastic wall, you touch the yield surface, and then basically you have softening towards large strain. So from this perspective, we have somehow characterized what is the behavior of our material from the laboratory scale. And also we were able to clarify what is the layering inside our subsoil. Now, the next step of our field case is designing actually how we want to bring this dyke to failure. So the water boards, which are the water authorities in the Netherlands, provide us some requirements for this failure. So first of all, we would like to bring to failure the outer slope of the dyke. So we are interested not in the failure of the outer slope, but we would like to force the failure, especially inside the pit layer, because the idea with this stress test is trying to get an understanding from the field point of view how this material, especially pit, behaves. And as well, we would like to collect as much of information as possible from the pre-failure and failure behavior, because as I mentioned before, we do not have only problem in terms of ultimate limit state, but we also have many problems in the Netherlands in terms of serviceability limit state. And therefore, the knowledge of the pre-failure behavior of this material is extremely important. So in order to satisfy these requirements, we basically design this type of failure mechanism. So we decide to excavate the toe of the dyke in order to fictitiously increase or double the height of our dyke. And we perform a series of dewatering at the toe of the dyke in such a way that we were able to gain information from both the pre-failure and the final, let's say, failure behavior. So we were able to perform a series of drawdowns the water is down, then we refill it, then we lower down again, refill it, and lower down again. In such a way, we were able to collect information throughout different stages of the test. Now, in order to collect information, we basically designed this test. You see here the wetting system that we place at the top of the dike in order to test the material in wet condition, which are the most, let's say, critical for the Netherlands. Here you see an impression of the excavation of the toe of the dike. And here you see basically one of the stage of the dewatering. So we were basically lowering down the water table inside the excavated area at the toe of the dike. Now here is the intensive, let's say, monitoring instrumentation. As Amin mentioned before, we install 3 lines of inclinometers, so in order to track the horizontal displacement. Pore water pressure transducer in such a way that we are able to record also the change in the pore water pressure during the pre-failure and the failure mechanism. But also, and it's quite important, we also install extensometer. The extensometer were basically anchors that we place at the interface between the different layers, so between the bottom of the dike and the top of the clay silt, and so on, in such a way that we were not able to reconstruct the horizontal displacement, but also the vertical displacement on the different layers. And we will see later on why this information was quite useful for us in understanding the behavior of these soils. This is basically an impression on how the slope basically looked like before the failure. So you see here, we have the water level in the canal. This is the excavated area at the toe of the dike, and here basically is our slope fully instrumented. We basically were able to bring the sample to failure. So you see here that actually the failure was not extending throughout the entire, let's say, longitudinal section, but was basically localized between the section south and the section center. And approximately it has an extent of 15 meters. The failure was basically composed by a 3D mechanism. So we have a lateral spreading at the toe of the dike, followed by an inward basically collapse of the crest of the dike. So you can see here a picture of the failure. The failure was happening very early in the morning, like 6 in the morning. So the picture were not, let's say, very easy. And here basically is a short video. I hope that you can see the video. It's very short. This is basically the moment of the failure. I try the video. Let's see if it works. Hope the video is working. So you see basically only part of the section collapsed. And this is basically a cross section with all the different measurements in terms of inclinometer. So the failure was basically composed by a sub-horizontal movement started at the toe of the dike and then retrogressively propagating towards the crest of the dike. Here you see basically a very large displacement of the pit, which is extremely important. If you remember before, I was trying to suggest that you keep in mind what was basically the profile of the water content in situ. So you can clearly see that the profile of the water content somehow provide an indication of what was the failure surface. You see here that we reconstructed the shear strain at the incipit of failure. And by looking at the lateral displacement inside the clayey silt layer, we were able to estimate that just before failure, the shear strain were actually about 5%. So 5% was basically the shear strain inside the clayey silt layer that basically brought the sample to failure. Now, why did I mention that having information both on the lateral displacement but also in the vertical displacement was important for us? As you remember, we were trying to test with this field stress test how different material basically deforms and behave in the field. So by combining the information from the inclinometers and the extensometer, we were able to define small blocks of material. So block B1, which is a block of peat, another block of peat below the crest of the dike, and one big block of clay. And by looking or by combining the horizontal displacement and the vertical displacement, we could reconstruct what we call volumetric strain in a 2D plane strain approach. And this is extremely important because this gave us the information to try to understand how these actually blocks of samples deforms in the field. So here I want to show you on the left-hand side, the block of peat. You can clearly see that the failure mechanism is basically described by a very important lateral bulging. You see that the dashed line is the initial shape of the block of peat. And basically, if you follow the deformation mode, you see that the block of peat basically bulged horizontally due to the very high compressibility of this layer, followed by a small vertical, let's say, squeeze. At the same time, the behavior of the clayey silt layer is completely different. So by combining, again, the lateral displacement and the vertical displacement, we could see that the clayey silt layer behaves similar like a direct simple shear test, but however, there was a small dilation. So it's a direct simple shear test, not at constant height. So having an insight on the failure mode of the different layers in the field was extremely important for us, because with this information, we could also assess which type of test in the laboratory is representative more of the failure mechanism. So for a clayey silt material, we can assume that a simple shear, though not necessarily the constant height, is quite good enough. However, if you look at the peat at the toe, a direct simple shear test might not be the most suitable test for peat, because this lateral bulging could be better mimicked by a triaxial compression test, or even better, now we are basically placing a lot of efforts in Delft to try to use biaxial apparatus to actually impose a plane strain lateral bulging inside peat. And having the knowledge of the failure mode of this material, from my opinion, is extremely important, because especially peat, in my opinion, is a fabric sensitive material. So we often speak about stress path, but for this material, which contains a lot of fibers, in my opinion, it's more appropriate speaking about strain path. So if you look here on the bottom right, you can imagine a sample of peat with a randomly distributed fibers. And you can imagine that if you impose an isotropic compression test, you're basically squeezing the fibers from a lateral point of view. So the fibers are not activated much. But on the other way around, if you impose an isochoric stress path, which means a triaxial and drain compression test, you are actually promoting lateral bulging and therefore stretching on our fiber. So that's why the knowledge of the type of failure in the field is extremely important, because it will guide us on which type of laboratory test we want to place inside our test program. And speaking about fibers, testing peat at the laboratory scale is extremely complex. It's complex because peat is not a simple soil. There is very much uncertainty in how we can derive shear strength parameter for peat. So here I want to show you an example of a fibrous peat sample tested as undrained triaxial compression test. So you clearly see that the deviatoric stress keeps increasing and almost reach the tension cutoff line. The tension cutoff line, for those of you who are not familiar with, is a line in which the horizontal effective stress is equal to 0. So if you transfer a tension cutoff line into friction angle, you ended up with a material with 90 degrees of friction angle, which obviously doesn't make sense in terms of assessment process. We cannot assume a material with 90 degrees of friction angle when we are performing our assessment stability analysis. So the idea here is just to show you how the behavior of peat could be better captured if assume that peat is a composite soil. So peat is at least an overimposition of a matrix, which is basically characterized by a very small fibers, but also by big fibers that provide an additional confinement to the sample. So and this is the results of a constitutive model that we have been developed here in Delft. So you see that the matrix, which is the red dashed line, already reached critical state for a friction angle of about 42 degrees. But if you overlap the contribution of the fibers, the overall stress strain path of our soil composite is much higher. So even though the matrix is already at failure, due to the additional confinement of the fibers, the overall impression that you get from laboratory tests that this material is much stronger. And this is true both in terms of the deviatoric stress response that you can see here on the left-hand side, but also, and more importantly, in terms of pore water pressure. So you have an additional increase in pore water pressure compared to the matrix due to these additional confinements of the fibers. Now, having an insight of how pit behaves, how the clay silt behave, is extremely important, because when you go back to the field, you need to imagine that these two materials, pit and silty clay, are not substantially isolated, but they are somehow communicating. And here on the left-hand side, you see an impression of an actual interface between a pit layer and a clay silty layer. So you see that we have a pit layer on the above, which is this dark material. And this pit layer is actually linked through a network of fibers. You see here these yellowish fibers with the clayly silt layer. Now, if you try to test these three materials, pit, clayly silt, and actually the interface in a direct simple shear test, you can clearly see a completely different stress-strain response. So the pit layer, which is basically the green stress-strain response, continuously show strain hardening, so you don't reach failure, even at shear strain of about 15%. But if you look at the interface, which is actually the blue line, already at 5% of shear strain, this material already mobilized the maximum stress ratio. And 5% was actually the shear strain at failure that we estimate from the field test. So having an insight from the laboratory point of view with the different kinematic compatibility between the different layers is extremely important. And this kinematic compatibility, in our opinion, comes from the role of fiber. So this lateral displacement that you saw inside the pit layer was basically transferred to the clayly silt through this kinematic constraint of the fibers. And the clayly silt layer reached failure much earlier than the pit due to a completely different stress-strain response. Now, to close the presentation, I would just want to give you a brief insight of what are now the current research that we are busy with. So a lot of attention has been dedicated with this field stress test to the actual behavior of this material, especially in fully saturated condition. But as mentioned by Suzanne this morning, a lot of problems nowadays comes from climate stresses. And in particular, for organic soil, I like distinguishing between two broad categories of climate stresses. So we have the classic unsaturated soil, shrinkage and swelling due to drying and wetting cycles, with formation, for example, here of desiccation cracks on our dikes and flood defense infrastructure. But actually for peat and especially highly organic material, there is another problem related to climate stresses, which is the degradation of this material. There is production of gas, which is coming from the biological degradation of this material, promoted also by increasing temperature. And actually peat developed gas. So inside our peat layer, we often see bubbles of methane and carbon dioxide. And here we call it gassy soil. So there are some conceptual differences between unsaturated and gassy soil. I just want to show you one small example of a recent experimental investigation that we have been conducting here. So we try to evaluate what are the implications of having gas bubble inside our soil. So here we generate artificially some CO2 bubbles inside our peat layer, and we perform triaxial and drain compression tests on actually samples containing a different amount of gas. These tests were containing basically between 5 to 10% of gas in terms of volume. I want to show you what does it mean having gas inside our soil. So you see here the mobilized friction angle at two different levels of strain, 2% and 5%. The white dot is basically the friction angle of peat at 2% without any gas, so it's about 20 degrees. And at 5% of axial strain, the friction angle is about 35 degrees. But if you account for the presence of gas, so you assume that inside your sample you have gas, you clearly see a reduction of friction angle. So the presence of gas in peat is actually reducing the mobilized shear strength. And the reason is because the strain that you are imposing to your sample are actually part of this strain are actually used to compress the pore fluid, which now contains gas, and only a minor part will go actually in stretching your material. So accounting for the presence of climate stresses, in particular gas, is a quite new challenge that we are now facing in our environment. Now, to conclude this presentation, the field test, in our opinion, is a unique opportunity to gain knowledge on the behavior of a geotechnical system as an overall, and in particular on the interaction between the different layers, and especially the kinematic compatibility at the interfaces between layers. But as Amin mentioned before, a combination of multiple sensor technology, inclinometers, extensometer, and pore water pressure can actually give you an insight on the coupled hydromechanical behavior. And at the same time is a unique source of information for numerical modeling. But at the same time, a field test must always be accompanied by laboratory tests. And in particular, laboratory tests are fundamental for not only designing the stress test itself, but also to understand and interpret the field monitoring data. Now, to conclude this presentation, I want to acknowledge all the people, including Amin, that actually work on this very nice case of study. And thank you very much for your attention.
Thank you, Stefano. I think both Stefano and Amin's talk gave us a quite good example of how the understanding of element can contribute to the interpretation and design of the field testing. So I think now any question from the audience?
Yeah, sure. I have a question for both. Very nice presentations, excellent, both of you. Very interesting. Why does it always fail the slope? Why does it fail at night?
Thank you, Yanis. That's a very nice question. We actually aim to fail around 8 in the morning, but actually was earlier, but we were lucky enough that there were people there to take picture and video. So we need to do better for the next time.
I think it has something to do with the moon. I have no
No,
explanation.
it is a funny question, of course, obviously, and everybody's laughing. I was laughing myself when I was thinking about it. But does it have to do perhaps anything with vegetation, the trees? I don't know. Or the statistical, let's say, data of 2 out of 2 is not enough?
I think the second.
The second.
Yes.
Okay, thank you.
Any other question?
Okay, so my question relates to these gassy soils, which Stefano presented. So when we introduce gas into these soils, is this gas dissolved in the pore fluid, or is it introduced into the air voids?
Yeah, thank you for the question. We actually flush the sample with water. Inside the water was dissolved CO2, and then we reduce the cell water pressure in undrained condition in order to exsolve basically the gas. Because for us was also quite important to actually assess if the exsolution process could have caused some softening on the soil fabrics. So we are not flushing gas directly, but we are flushing dissolved gas and then exsolving gas by reducing the confining cell pressure in undrained condition.
The tests were in saturated condition.
Sorry?
The tests were in saturated condition or unsaturated?
When we performed the flushing, the sample was fully saturated. After the gas generation, we basically test unsaturated conditions or gassy conditions. So the degree of saturation when we performed the final steering stage was ranging between 87 to 92%, depending on the amount of gas that we were able to generate.
Any other question?
Thanks for the presentation, and your project is wonderful. What would be your advice to the practitioners, how they should react when they get the results of laboratory testing of peat with the 55 degrees friction angle, for example? So should we use it or somehow discuss it with the laboratory?
Yes, that's a very tricky question. Let's say there are 2 points of view. The current approach in the Netherlands could be considered also over-conservative, because if I look at the, let's say, the Eurocode transfer in the Netherlands, the friction angle for peat is given by 15 degrees, which I understand is conservative, but it seems really over-conservative. Now, for what concern which kind of friction angle we want to use in the practice, that's a matter of discussion. It depends on which type of, let's say, problem you're facing. If it is a problem where you are looking at the ultimate state or serviceability limit state. So in my opinion, I'm not able to give you really a number because it depends from several factors, but definitely 15 degrees of friction angle seems over-conservative. At the same time, 60 or 70 degrees of friction angle are not realistic. The question is how much, in my opinion, can we trust on the fiber's contribution in the field? So how much are we able to engage the fibers in a field application? Because obviously the fibers give you quite a side effects, which is basically size effects. So the fibers, which is 5 centimeters long, might count a lot in a sample which is 10 centimeters in diameter. But what about the size effects of the same fibers in the field when you're actually looking at a problem which has scale completely different from the laboratory? So the best way to tackle this problem to me is including in a constitutive model the role of fibers, and trying to assess by back analyzing laboratory data how we can include or not the fibers.
Thank you.
I might answer posing one question than answer, but it's an open issue at the moment.
One more question for Amin.
Yes.
You showed that there is a clear difference when you have vegetation and when you don't have vegetation. I'm talking about your centrifuge experiment. Is it the 4 kilopascal cohesion only, or is it also the fact that the vegetation perhaps is sucking water? Like,
yeah, indeed. In long term, vegetation has two effects. One of them is mechanical reinforcement. The other one is changing the hydraulic regime around the roots. In my case, because the rain duration was scaled by a factor of 1/n2. So this sucking of the water was not really did not play a role. But indeed, in reality, it does. Yeah. And also for my centrifuge test, because I wanted to have a comparable surface with the unvegetated soil, I cut the leaves. So when you cut the leaves, basically you also, I believe, eliminate the tendency for suction from the roots as well. Yeah.
Okay, any more questions?
What about the scaling effect for the reeds? You also test not in the centrifuge with the same roots, but I think you wanted to model the tree roots or original model.
I guess this question is very similar to simulation of peat, because you basically, by simulating a rooted centrifuge element, you are adding some natural fibers to the sample, and by basically this you cannot. So the scaling effect for the root diameter is not n. In normal centrifuge scaling factor, we say that the geometry, linear geometry, is multiplied by n to get the prototype. But in this case, I believe it's not correct, because you are basically testing a global bulk behavior of a material that has some fibers inside. Therefore, you cannot say that this was actually this oat, this Avena sativa, had a mean diameter after, I think, 28 days of about 1 millimeter, and I performed the test at 50 G, so I cannot say that this root was I don't know, a 50 millimeter root in the reality in Rüdlingen.
So it belongs to the material.
Yeah.
That's all for this morning. So I think I will just close this session and thank you, Arvin and Stefano, for the nice presentation. And we will